Probably one of the most sort of powerful techniques is, or a powerful measurement rather, is a phase curve. For many of these exoplanets, at least the ones that we can sort of measure the most easily, the hot Jupiters, these things are very close to their parent star, so they become tidally locked. What that means is the gravitational pull from this star onto this planet is really, really huge. So if this planet is sort of trying to rotate at all, it's going to feel that pull, that gravitational pull. So it kind of gets locked into a synchronous rotation, where as it's orbiting, it's rotating at exactly the same speed. So it has one side facing the star at all times, much like the moon and the Earth.
With the phase curve, what we do is we study the light of the star and the planet together, and we watch as the planet orbits around the star. And from our point of view on Earth, what we see is the planet go from the bright, hot day side, and as it orbits around, then you see the cool, dim night side. And so the actual amount of light you will see will modulate. The star is basically the same, and you will see the planet rise up and down as you see from the hot side to the night side. And from this, we can learn about how hot the day side is and how cool the night side is, and actually make a whole temperature map of the entire planet as it goes around the star.
If we watch the luminosity or the brightness of this whole system, the starlight isn't really changing. That's roughly the same, especially if we can sort of account for anything that might change the starlight, like star spots or rotation of the star. But the planet, on the other hand, when it's in this position, for example, it's going to be much brighter. It has a day side, which is going to be emitting a lot of light, whereas when it's rotated around to here, there's a night side and it's not going to be as bright. So by observing that change in brightness of this whole system, planet and star system, we can learn about the temperature gradients in the atmosphere. And that's really important because we know from Earth's atmosphere that the sort of engine, the most important sort of driving parameter, among a few others, is the temperature gradient between the equator to pole. That's the sort of engine that pushes the Earth's atmosphere in many ways. So if we have this same information from an exoplanet, it really helps us to understand them and to sort of set our models up. Transmission spectroscopy is a really powerful technique which really allows us to look into the atmosphere directly of these exoplanets. Quite a lot of the things where we take measurements of exoplanets, radial velocity, etc., we learn bulk parameters. But transmission spectroscopy gives us a glimpse of what's going on in the atmosphere itself. Now, as this planet sort of moves in front of its star, the amount of light it blocks out, as we know from transits, is going to depend on its radius. But we also know that at different wavelengths, different sort of species interact with the light differently. So what that means is that if we look at different wavelengths, we'll see different radius, and therefore we might be able to detect what that planet is made of, what the composition of its atmosphere is. So that gives us two things really. First of all, it tells us, for example, it might tell us individual species. Is there sodium in this atmosphere, for example, has been discovered in quite a few, or potassium. But perhaps kind of more interestingly from a theoretical point of view is there's been a lot of work recently on how cloudy these atmospheres are or how hazy. When we have this technique and the light sort of grazes through the atmosphere, you can imagine that if there are clouds present or hazes in the atmosphere that might scatter or block the light, we instantly see that. It sticks out like a sore thumb. It's a very clear signal. And we know that from modelling the Earth, clouds are very, very complicated and they change everything and they're very hard to model. So the opportunity to have these observations directly tell us what clouds are like in the atmosphere of a planet, many tens of light years away is really exciting. And really to understand how those clouds form, why they exist, where we detect them, if you like, and also probably more interesting is why in some cases they aren't there. That's a real challenge, and that's something where the observations are informing the models, and the models are then trying to interpret those observations. So in a few cases, there's even been estimates of the wind speeds in the atmosphere of some of these exoplanets, which is really kind of cool. We can estimate the wind speed in the atmosphere of a planet, sort of 60, 70 light years away, which is pretty amazing. And the way that's done is this same sort of Doppler shifting technique, essentially, the same wobble that we see as a planet orbits around its star. We can also use that to look at signatures from the atmosphere itself using a very, very big telescope, and we can try to back out shifts in that atmospheric signature. that might be caused by the wind itself. So it's a really difficult technique to do, but it has been done in a couple of cases, and that's given us some sort of constraint on our models. It sort of helps us understand if the models are giving the right answer. Another key thing about the dynamics in the exoplanets, particularly hot Jupiters, is that we know the hottest part of this atmosphere, sort of from first principles or your first guess. You might think that it's the bit that's closest to the star. That makes sense, that should be the hottest part. But what we've discovered is actually the hottest part of the atmosphere is slightly shifted. And one of the reasons for this, the most likely reason, is probably that these winds themselves are shifting the heat. They're actually shifting the heat away from that point and transferring it. This is also confirmed by the direct measurements of wind speeds themselves. So it gives us a real confidence that our models, which don't forget are originally designed for Earth at 300 Kelvin or so, with an Earth-like atmosphere, and now we're using them to study things at a few thousand degrees C and wind speeds of several kilometers per second. This sort of collection of observations and comparisons gives us a lot of confidence that what we're doing is correct, and we're starting to really understand these atmospheres.
So I have a demo to illustrate how transmission spectroscopy works for exoplanets. And what we have here is the illustration of our starlight. And with transmission spectra, we wait for a transit to happen, so a planet to pass in front of the star. And of course, when that happens, this planet will block out some of the starlight, and we could actually measure directly how big that planet is, simply by counting up the starlight beforehand, and then when the planet's blocking some of the light, then we count up how much is lost. So we can already tell how big the planet is, but we can go further, because actually the atmosphere will play a role too. So if we have a planet with an extended atmosphere, so in this case it will be a planet with a red sunset, some of the light will filter through the atmosphere and leave its spectral imprint. And what we can do is actually look at different wavelengths and look to see how large that planet is at different wavelengths, and we can back out the composition this way. So I'll illustrate it. When we go to our telescope and we put in a red filter, essentially what will happen is the red light will come from the star, go through the planet's atmosphere, go through our red filter in our telescope, and you'll simply measure the bulk planet itself with our planet with the red sunset. If we then switch to a different filter, let's say we look in blue light, what happens is the planet looks very much larger. So at blue wavelengths, the atoms and the molecules are scattering the light out of our field of view, and the planet looks larger. So by looking at many different wavelengths, we can see how large the planet is, and we can construct what's called a transmission spectrum, or you can also think of it as an absorption spectrum. So you can learn about the composition of those different atoms and molecules that are absorbing the light, and the spectral imprint is left by the actual wavelengths that those occur at. So it's really the multi-wavelength nature, which is the power of transmission spectroscopy, where you can see the planet look bigger or smaller depending on which wavelength you look at.